Good evening, and welcome to the second lecture in the Carnegie Observatories 2021 Astronomy and Astrophysics Lecture Series. I'm Dr. John Mulcahy. I'm the director of the Carnegie Observatories, and I'm the science deputy for the Carnegie Institution for Science. I want to start by just thanking many of you for your messages about my broken ankle, which many people noticed last time I had a big boot on my leg. It's doing better, and I'm now down to just an ankle support here, so I hope to be dancing by the fourth lecture. I want to start by acknowledging, as always, our financial support we receive for this lecture series from the Norris Foundation and for our friends at the Huntington Library who have helped host us here in this beautiful auditorium today. Our speaker today is Tom Holoien. Tom did his PhD work at Ohio State University. He then came to Carnegie as a prestigious Carnegie postdoctoral fellow. And last year, Tom was awarded a NASA Hubble Fellowship to continue his work at Carnegie. Tom is an expert on many things that go boom, particularly supernova remnants, but his other specialty is the one you're going to hear a lot about tonight, which is things that are called tidal disruptive events. These are events when black holes eat stars or gas clouds. It's a really exciting topic. And many of you may have seen Tom. He was featured in NASA's Black Hole Week back in 2019 and did a lot of press interviews for that, which some of that work you're going to hear about today. So without further ado, let me welcome to the stage Tom Holoien. Tom.
All right. Well, thank you very much for that lovely introduction, John, and thank you everybody for being here virtually to hear me speak about my work and things that I'm passionate about. I feel really privileged to be here, so thank you again for the opportunity. Now, as John said, I primarily study observationally dying stars. So when stars die, they usually explode in these violent, energetic explosions. And I use telescopes all around the globe to study the light coming from these explosions and use that to learn about the physics that's going on behind them. Now, the most common thing I study, as John said, is called a supernova. These happen when a massive star reaches the end of its lifetime. But I also study stars that die in less common ways. And one of these is getting eaten by a black hole, something that we call a tidal disruption event, or a TDE. So today I'm going to tell you a little bit about what happens when one of these TDEs occurs and how we can use them to study supermassive black holes. But before that, I'm going to spend a little bit of time talking about black holes themselves. What are they? What do we think that we know about them? And how do we actually study them? And as a caveat before I begin, I just want to say that most of the images and videos that I'm going to be showing today are artist renditions or simulations, because unfortunately these things are often much too faint or too far away for us to actually take pictures of them. Okay, so let's jump in. You've probably heard of black holes because they are invoked in popular culture all the time. From shows like Star Trek to Stargate to movies like Event Horizon and Interstellar, which is incidentally where the background of my slide comes from. And based on shows and movies like these, you might have this image of black holes as being this destructive force that consumes everything around them. Or if you fell into one, you might get transported to another place or time or even reality. The Simpsons even did a Halloween episode where Homer falls through a black hole and ends up in our world. But this all sounds very fantastical, so what are black holes really? And to answer that, I'm actually going to have to tell you a little bit about general relativity. Now, general relativity is something you might have heard of. You might even associate it with the man who came up with it, Albert Einstein. But you probably don't know much about what it is or how it relates to black holes. You might even be a little bit worried that this talk might get a little bit too technical or go over your head, and you're not alone. When I tried to explain this to my son, he actually was not a big fan. But don't worry, he eventually came around, and as I mentioned before, I'm an observational astronomer. That means that my job basically boils down to using cameras that are attached to really big lenses to take pretty pictures of the sky. So I'm going to give you the basic observational astronomer's version of general relativity and leave all the complicated math to the theoretical physicists, okay? Please also keep this in mind when you ask me follow-up questions. Okay, so general relativity was developed in order to help explain gravity. And as you might remember from school, the generally accepted version of gravity that we have was come up with by Isaac Newton back in the 1600s. And his theory says that all matter, all objects with mass, have a force that attracts other matter towards them. This force gets stronger as the masses get bigger, and it gets weaker as the masses move further apart. And this theory explains things pretty well. It explains why we stay on the Earth and don't float off into space, explains why the moon goes in orbit around the Earth and why the Earth orbits the sun, and so on and so forth. But after a couple of centuries, scientists were starting to find things, to observe things that weren't quite explained by Newton's version of gravity. And it also leaves a key piece of information out. What is this force between objects that pulls them together? Why does this happen? And this was something that Newton had thought about, but ultimately was unable to answer. As he wrote, "I leave this to the consideration of my readers." So this is where Albert Einstein comes in. In the early 1900s, Einstein was thinking about gravity, and he had what he allegedly called the happiest thought of his life. He imagined a man falling off of a roof. And when he thought about this, he realized that while gravity would be pulling this man down, once he's in free fall, he would feel weightless. And this led him to formulate what he called the equivalence principle. Okay? So let's imagine that we have an elevator or just a box with no windows on Earth, as in the right-hand picture here. As this elevator goes downward, the person inside would feel weightlessness. Similarly, if we had someone out in space in a spaceship, just floating far away from all the massive objects that are out there, that person would also feel weightlessness. So putting this another way, absent any other information, without a window to look out and see what's going on around you, there's no way to tell whether you're floating in the middle of empty space or in free fall towards a massive object like a planet. Now, if we imagine that our box on Earth has reached the ground and the person is standing in it, feeling their weight, but then we accelerate our spaceship at the same rate that gravity pulls us here on Earth, 9.8 meters per second, the person in the spaceship would actually weigh exactly the same as they do here. And if they threw a ball, it would follow the exact same trajectory as it does on Earth. So this is what the equivalence principle says. Gravity is actually indistinguishable from acceleration, okay? And it was this realization that led Einstein to start thinking about how this could be true and how matter could be creating this acceleration-like effect. But it wasn't all that he needed. He happened to be working on the time on some explorations of curved geometries, curved surfaces. So, you know, if you are on a flat surface, like a two-dimensional plane, like I have on the left here, if two people started walking in a parallel direction, they would keep going on in straight lines and they would never ever meet each other, right? It's a flat plane, they're straight lines, they'll never intersect. But on a curved surface, this isn't necessarily true. So imagine, for instance, the surface of a sphere. If two people are moving in the same direction initially, say they start going north, they'll be parallel at first, but eventually they're going to meet at the North Pole. So these curved surfaces can distort straight lines. They can distort the motion of things that are moving on them. And the shortest distance between 2 points might not necessarily be a straight line anymore. So Einstein spent 7 years thinking about gravity, the equivalence principle, and these curved geometries. And finally, he developed a series of equations that describe how matter affects space-time and creates the effect of gravity. He called this the general theory of relativity. And boiling it down, basically what it says is that mass curves nearby space-time, and the observed gravitational force is caused by moving in the space-time that has been curved by a massive object. Or to borrow a less clunky phrasing from John Wheeler, space-time tells matter how to move, matter tells space-time how to curve. So to describe what this means, we usually use something that we call the trampoline model. So imagine we have a trampoline, and the surface of this trampoline is going to be our 2D representation of space-time. If I roll a marble across the trampoline, it's just going to go in a straight line straight across it. Just like if you were out in space and moving nowhere near anything massive, you would just continue on in a straight line. However, if we put a bowling ball in the middle of the trampoline, it's going to distort the surface of the trampoline. It's going to pull it down. So now if I roll my marble on the exact same path that I started with before, it's no longer going to go straight across. It's going to curve. It's going to follow a path along this curved surface that the bowling ball is creating. And it's going to move around it and towards it. So my diagram here is a little bit clunky, so let's look at an animation. So basically, all these small marbles are just following paths along this curved surface of the trampoline that's being created by this massive object in the middle. So this is what's happening to create what we perceive as gravity. A massive object like Earth is distorting the space-time around it, and other objects like us are just inside that curved space-time and being moved towards it because of that. So here's a sort of grid view of what I'm talking about, just to show this distortion a little bit better. And obviously this analogy has some issues. Most glaringly, it's two-dimensional and space is three-dimensional. So it might actually look something like this, but this is a little bit confusing to look at. It's hard to visualize how this would be affecting the paths of things around it. So I'm gonna stick with the 2D version, the simpler version here. Just remember that this is an approximation, okay? Now you might have a few questions. Things like, why is it called general relativity? Or why does this matter? Well, to answer the first question, general relativity describes how measurements of space and time can differ if you are moving relative to someone else. So think about cars on the freeway. From an outside observer, you might see two cars going opposite directions, both going 70 miles an hour. Probably not in LA, but you can imagine what this would look like. Now, if you're in one of those cars, you might feel that you're not moving, but the car moving towards you is moving 140 miles an hour the other direction, right? Now, if you start to introduce accelerations or really large masses or speeds close to the speed of light, this gets really complicated. But this is a simple example of how the observations of one person in one frame of reference, so the person who's not in a car outside, can differ from those observations made by someone who is moving inside the car. So this is how these measurements can be thought of as relative to one another. Now, the second question is a little more difficult one. You might say, okay, I can accept this idea that mass curves space-time, and that's great, but why does it matter for me here on Earth? Isn't Newton's version good enough? And yeah, that's probably true most of the time. Newton's version of gravity is basically a good approximation of what general relativity would tell you. And for everything you're experiencing here on Earth, for the most part, and also most things that we look at in space, Newton's version is going to be good enough. But there are certain things that it can't explain. So for example, the orbit of Mercury. So it turns out that while Mercury goes around the sun in this elliptical orbit, its orbit itself actually rotates as well. Think of like a person using a hula hoop. The part that's closest to the person is moving. So we call this precession, and Newton's version of gravity can't explain this. But in general relativity, it's very simple. Mercury is just following a specific path in the space-time that's being curved by the sun. Newton's version of gravity also has trouble explaining something we call gravitational lensing, which is how light is actually bent and distorted by gravity. So imagine you have something really massive out in space, like a cluster of galaxies. On the other side of that is something else that emits light, something like a galaxy. So like this diagram here on the left. As the light from this background galaxy comes towards us here on Earth, it can't just move straight towards us. We can't observe it directly. What happens is that it gets bent because the space-time around this cluster is extremely distorted because it's very massive. So what we end up with is something like this picture on the right, which is from the Hubble Space Telescope. And you see these curved shapes, these arcs in the image here. These are all background galaxies, things that are behind this cluster that is imaged here. And their light is being distorted and stretched into these weird shapes because of the gravity caused by this cluster. So again, general relativity can explain this easily because the particles of light, these photons from these background galaxies, are just moving along curved spacetime. And finally, we have something called gravitational time dilation. Now, you've heard me saying space-time throughout all of this, and you might be saying, okay, I get space being curved, but what does this have to do with time? Well, it turns out that just like how massive objects distort space around them, they also distort the time near them. Time moves slower the closer you are to something massive. And this sounds crazy, but it's actually true. We have measured that clocks on the International Space Station, for example, actually move faster than clocks here on Earth. And you might think this doesn't have anything to do with you, but it actually affects your everyday life. Think about something like a GPS satellite. If we didn't know about this effect of general relativity and correct for it for the clocks on those satellites, we wouldn't actually get accurate information in our GPS apps, and you might end up in the wrong place at the wrong time. So if we want to fully understand the effects of gravity and fully understand what we're looking at in the universe, we need general relativity. All right, so now you're all experts on general relativity, so I can finally explain to you what a black hole is, because it comes directly from this idea of general relativity. So let's imagine the sun sitting out here in space, distorting and curving the space-time around it, like in this image. I'm going to define a couple of terms here. So we'll call this distorted space around the sun's gravity well, because it kind of looks like a well on Earth. If you had a temperature-resistant suit and you stood on the surface of the sun, we'd say you're at the bottom of the sun's gravity well. Now, if you wanted to get out of that gravity well and escape off into space that's unaffected by the sun, you need to move a certain velocity. We call this the escape velocity. Makes sense? Now, let's imagine what would happen if we increase the mass of the sun. Well, that's pretty easy to visualize. If you double the weight of that bowling ball on the trampoline, it's going to pull it down more, so the gravity well will become deeper as the mass goes up. And because it's deeper, it's harder to get out. The escape velocity will also go up. But this is also true if we make the object in the middle smaller. So if we leave the mass the same, but we make it a smaller thing. So for example, let's take our bowling ball and crush it down to the size of a marble. It would pull harder right at the center of its mass. It would pull further down. So if the radius of this object gets smaller, the gravity well gets deeper, and the escape velocity goes up. So this is what's important for understanding black holes, okay? So back to the sun. The sun's mass is about 2 times 10 to the 30 kilograms, so 2 million trillion kilograms. It's pretty big. And its radius is about 700,000 kilometers, so it's about 100 times the radius of the Earth. Its escape velocity is about 600 kilometers per second. So that's pretty fast. It's a lot faster than anything's moving here on Earth for the most part. But let's imagine we want to crunch the sun down. Let's squeeze it so hard so it gets smaller and smaller until all the atoms that make up the sun are rubbing against each other and their electrons are repelling each other. And that keeps us from squeezing it any further. This is something we call a white dwarf. So if we leave the mass the same, but we squeeze the sun down to a white dwarf, its radius would be about 7,000 kilometers, so it'll be about the size of the Earth. And its escape velocity is going to go up because the gravity well gets deeper. So the escape velocity now is going to be about 6,200 kilometers per second. Let's keep going. Let's push so hard, we force all those electrons and protons together, we make a giant ball of neutrons that resists being pushed any further because of some quantum physical effects and some nuclear forces. This is something we call a neutron star, okay? Now, if we left the mass of the sun the same, our neutron star that we made out of the sun, it's only going to be about 10 kilometers in radius. It would fit between here and Griffith Observatory, for example. So extremely small object for how much mass is packed in there. As you can imagine, this has pretty strong effects. The escape velocity goes up to 160,000 kilometers per second, so about half the speed of light. Now, let's take this to the extreme. Let's keep squeezing the sun down until all of its mass gets forced into a single point. Its radius becomes vanishingly tiny, something that we call a singularity. Because the escape velocity goes up as the radius goes down, if the radius basically goes to 0, the escape velocity is effectively going to become infinite. This is what we call a black hole. It's something that's so compact that it's impossible to get out of the gravity well. And in fact, you don't even have to be at the bottom of this to be stuck inside it, because we have a cosmic speed limit. Nothing in the universe can move faster than the speed of light. So as you go down this gravity well, the escape velocity is going to be going higher and higher, and eventually you're going to reach a point where from the center of this singularity, where the escape velocity is equal to the speed of light. This is something that we call the event horizon. And once you reach this distance from a singularity, space is so distorted that nothing, not even light, can escape. So for our crushed down sun, it would be about 3 kilometers. And because no light can get out, if we could see one of these objects, what we would see is a dark sphere with a radius equal to the event horizon, a black hole in space. So this is what a black hole is and how it comes out of this idea of general relativity. And before I move on, I just want to clarify one thing. Now, we've been using this example of the sun being crushed down more and more to help illustrate what happens if you leave the mass the same but make something smaller. But this is not actually the path of what's going to happen to the sun in the future. In fact, stars will end up as one of these 3 things, depending on how big they are. So the sun is actually going to end up as a white dwarf eventually, a few billion years from now. But if it was more massive, maybe about 10 times as big, it could end up as a black hole. Now, I'm going to talk a little bit more about how black holes form in a little bit, but I just want to make sure that was clear that we're not in any danger of our sun suddenly turning into a black hole one day. So what would these black holes look like if we could see them? Well, we'd have this dark sphere about the size of the event horizon, right? And at the center of this, invisible to us, would be this singularity, this mass that's compressed down to an infinitely tiny volume. Now, when we talk about the mass of the black hole, what we're actually talking about is the mass of this singularity. All the matter that's inside eventually is going to get compressed down into it. And you can add more, but it's always going to stay the same size. The mass will go up, but the singularity itself is always vanishingly tiny. It's kind of hard to think about, but this is physically what's going on. However, as you add mass to the singularity, the event horizon is going to get larger. So when we talk about the mass of a black hole, we mean the mass of the singularity at the middle. But when we talk about the size, we usually mean the size of the event horizon. And the reason we often see black holes depicted as this gateway to other dimensions or times, a way to go back in time and things like that, is that we don't actually know really what would happen inside a singularity. When something is infinitely tiny, math and physics don't really make sense anymore. And theoretically, it's possible to show that you could have something like two regions of space connected to each other because they're so folded over that they touch, or time that gets so distorted it moves backwards. And because nothing can get out of a black hole, even if we had one right next door and could send probes inside it, we could never find out what's going on because they can't send signals back out to us. So it's this unknown, this unknowability of the singularity at the middle. That's why black holes are often used as a way to break the constraints of physics in these science fiction stories. Now, outside of the black hole, outside of this event horizon, we have a decent idea of what would be going on. Far away, actually, there wouldn't be much difference between a black hole and an object of similar mass. So for example, if we replace the sun with a black hole with the same mass, it would be a lot colder here on Earth, for sure. But the Earth itself would continue to orbit that black hole just like it orbits the sun. However, when you get close to the event horizon, space gets very distorted. And it actually gets so distorted that there's no longer a way to stably orbit the black hole. Basically, if you go inside this region of unstable space, you're either going to be ejected at a very high speed, or you're more likely probably going to fall in. So this is why black holes have this impression of eating up everything around them. It's because if stuff gets close to it, it's probably going to fall in. But remember, as long as you're outside of the event horizon, if you had a strong enough force to get you out, you could still escape. And just to show kind of what this might look like in reality, this is a rendering from NASA that depicts a black hole with a disk of material falling into it, something that we call an accretion disk. And as matter falls into a black hole, angular momentum actually causes it to flatten into a disk shape like this. Think about throwing a ball of pizza dough into the air. It's going to flatten and become round and flat like a disk. So we get this accretion disk, and what's actually happening here is you have a black hole with just a disk around it. There's nothing above or below it. But what's great about this, it illustrates the effects of gravitational lensing close to a black hole, which are very strong. The stuff that we see on top of the black hole here, the stuff that I'm pointing at with my pointer, is actually the back side of the disk that has been, the light has been bent up so that it looks like it's on top of the black hole. The stuff we see below it is the underside of the disk. So if I play this video, you'll see that it's rotating, and the point of view is going to rotate and show you what this disk might look like if we could see this from other angles. There we go. So you can see that near a black hole, the effects of gravitational lensing are very strong because the space is so distorted nearby. Okay. Now, up until now, I've been talking about black holes with the mass of the sun, but they actually come in a wide range of masses. And typically, we sort them into three sort of bins based on how massive they are. So up to about 100 solar masses, or 100 times the mass of the sun, we call this a stellar mass black hole, or a stellar black hole. These are basically the same mass as large stars. On the other end of the spectrum, we have what we call a supermassive black hole. These go from about 1,000,000 times the mass of the sun up to billions or even more. So these are really, really massive objects. In between these two extremes, we have something called an intermediate mass black hole, or an IMBH. And the reason there's a question mark on this figure here is because we actually don't know for sure that these IMBHs exist. We've never actually found one. And I'll talk a little bit about how we go looking for black holes in a couple minutes, but first I just want to go over how we think the black holes of various masses here might form. So for stellar mass black holes, we have a couple of different ways that we think they could form. The first of these is called core collapse. This happens at the end of a massive star's life. And basically what happens is that the core will implode on itself, as in this video here, And what will be left behind is either a neutron star or a black hole. And often what happens is the outer layers of the star get blown away in a big explosion called a supernova. What will be left behind then is the remnant, the black hole or the neutron star. And typically this would have the mass about equal to the core of that star that blew up. Now, this process of core collapse happens in a matter of seconds, but we'd have to wait for the star to evolve and reach this point. So to actually form black holes this way would probably take a few 100,000 years or even maybe up to 10 to 100 million years to happen. Now, the other way we think you can form these stellar mass black holes is through the merger of two neutron stars. So as two neutron stars get close to each other, they'll spiral together, as you see in this video here, faster and faster and faster, and finally they'll collide and explode in an explosion that we call a kilonova. Now, what's left behind would then be a black hole, roughly mass equal to the two neutron stars that merged into it. This process is much slower than the previous one, though, because not only do you have to wait for those neutron stars to form, which can take millions and millions of years, but then you have to wait for the two neutron stars to get close enough to move together. So probably this takes billions of years. Fortunately, our universe is quite old, 13, 14 billion years old, so we have plenty of time for this to have happened. We've actually seen this happen through our observations. Now, on the other end of the spectrum, these larger ones, we actually aren't sure how they form. As I said before, we still haven't found these intermediate mass ones at all. And we think that if they do exist, they might happen in these clusters of stars like what I'm showing on the left here. So at the centers of these clusters, there's a lot of stars packed together in a small region of space. And over time, it's possible they could merge together and get big enough to form an intermediate mass black hole. Now, supermassive black holes we have found. They live at the centers of big galaxies like our own, the Milky Way. But we don't know how these form either. In fact, they're so massive that it's actually hard to figure out how to get that much mass into such a small space in the age of the universe. One possible way we think this could happen is if there are lots of clusters near the center of a galaxy, way a long time ago, those clusters could form intermediate mass black holes and then kind of sink to the center, and all of those could merge together to form a supermassive black hole. So it could be sort of an iterative process here. But this is actually something we don't know, and one of the big unknowns around black holes that we're still trying to answer today. And because this process likely takes billions and billions of years, there's no way we can actually see it happen. We can only figure this out by looking at the black holes we see them as we see them today. So besides how they form, some other questions we have about black holes are some of the ones here. Do these intermediate mass black holes exist? And if so, where are they? What does the whole population of black holes look like for properties like their masses, for example? What could this tell us about how they form? We also want to know how black holes affect the things around them. What happens to material as it falls into a black hole? How do these accretion disks form, and what happens if they get disrupted or destroyed? So these are just some of the many questions we're trying to answer by looking at and studying black holes. And the object here is ultimately to just better understand our universe. Not only are black holes interesting places where lots of extreme physics happens, it's also related to the evolution of stars, the evolution of galaxies. So hopefully by answering these, we can learn more about how we got here. But to do this, we need to find and study more black holes, as I said. And you might be asking, if black holes are black and nothing can get out, how can we actually find them or study them? And that's a good question. And the answer is we don't observe the black holes directly. We observe the effects that they have on the stuff around them. So one way that we can do this is by looking at the gravitational effects they have. So this video is going to show the orbits of a whole bunch of stars at the center of our galaxy, as tracked by astronomers at UCLA. And the thing indicated by a star in the middle there is what's called Sagittarius A star, the massive thing at the center of our galaxy. So I'm going to start this video, and you can see as over time, we've been able to plot the paths of all of these stars around this thing in the middle. And this has let us build up a sort of three-dimensional map of how all these stars are moving, what their orbits look like. And by looking at these, we can calculate the mass of this thing at the center. It ends up being about 4 million times the mass of the sun. And because we know how big it is and how massive it is, we know because the only way to pack that much mass into such a tiny region of space is to have a black hole. We know that this must be a black hole. Since it's over 1 million solar masses, it's a supermassive black hole. In fact, we now think that most galaxies like the Milky Way have a supermassive black hole in their center. We can also use gravitational effects to study stellar mass black holes too. if they're in a binary system with a star, so if another star is orbiting around them, the light from that star will actually wobble a little bit because of the gravity from the black hole. So if we see that and can study that, we can learn about stellar mass black holes this way too. So another more recent way that we can find and study black holes is by looking for gravitational waves that come out of them as they merge. So similar to the merger of the two neutron stars I showed before, in this case, these are both black holes, and as they get closer and closer, they're stirring up the space around them and actually creating ripples that move away from them throughout space-time. And as they get closer and closer together, these ripples come out with faster and faster frequency. So if we detect this and see how it's changing, we can infer the masses of the black holes that went into it and what's left behind. And this is something we've actually been able to do just in the last decade. It's quite amazing. But by far the most common way we study black holes is by looking for the radiation, the light that comes out of them as they affect things around them. Sorry, not coming out of the black hole, I should clarify, coming out of the light, or coming out of the matter that's falling into the black hole. Now, in a stellar mass black hole, this typically would take the form of pulling in some matter from a star that's nearby, like in this left-hand picture here. As this matter falls towards the black hole, it'll form one of these accretion disks and it heats up. And this causes it to emit X-ray light. So we often call this an X-ray binary system. And the first ever black hole we ever detected was found in one of these systems in 1964. Now, for supermassive black holes, it turns out that the central regions of a lot of galaxies have stuff like gas and dust and other things in there. So if enough of this is close enough to the black hole to fall into it, to accrete onto it, it'll form one of these disks and emit a lot of very high energy light all across the electromagnetic spectrum. Now, we call this an active galactic nucleus, or an AGN. And here, active just means that it's in the process actively of gobbling up stuff around it, as opposed to not having anything near it and just sitting there being quiescent or dormant. Kind of think of it like a volcano. They're either active or they're dormant, but they could become active at any point. Now, in both cases here, you see that it has this big jet structure coming out of the poles of the black hole here. These can form as matter gets really close to the black hole. It gets accelerated, probably by magnetic fields, and this shoots out these big jets from the poles. And this releases a lot of high energy particles and light, and if these are happening, we can also detect that as well. So there's a lot of different light that we can see coming from black holes. Now, for the rest of my talk, I'm going to be focusing on these supermassive black holes. That's not to say that stellar mass ones aren't interesting, it's just that I spend most of my time studying the really big ones. Okay? So first I want to talk about these AGNs just a little bit more. These are our primary way of studying supermassive black holes because they're active and we can see light coming out of them. And we think most of them look like this. You have a black hole at the center, surrounded by this disk of material, this accretion disk falling into it. And then outside of that, we have a torus or donut shape of dusty stuff, neutral material. And as we look at an AGN, we can see the light coming from it, but we've observed that they look kind of different sometimes, and we think that these differences just come from the angle that we're looking at this system. If you see it from the edge, you're not seeing that accretion disk directly. The light is coming through this torus of material around it, and that causes it to look a little bit different. Whereas if we look at it face on, we'll see that light from the disk straight up. Now, by looking at how the light from this disk is changing a little bit over time, perhaps because a little bit more material got fed into the black hole in a short period of time, or something nearby disrupted that disk a little bit, we can use those little changes in the light to measure things like how massive the black hole is. And we've now detected many AGNs. These are a couple pictures from Hubble in the optical light where you can see the galaxy. And then overlaid on top of that are images of these big jets. And you can see that in both cases, these galaxies are launching jets that are many times the size of the galaxy themselves. So there's a lot of energy here. And in the case on the right, we've actually been able to zoom in and see this torus region around the black hole in the center. So we think our picture here is pretty good, and we've been able to use them to study black holes. But the problem is, the big problem is that most supermassive black holes are not active. In fact, it's only a very small percentage of them. And because of this, our sample of supermassive black holes that we can actually study with AGNs is pretty small, and it's limited to only these ones that are actively doing stuff. Furthermore, these systems, these disks, are pretty stable for long periods of time. We can't, for example, see them form or get disrupted or get destroyed because this process takes millions and millions of years. So if we want to see something like an accretion disk form or see a jet get launched, we have to find something else, something that forms and evolves on observable timescales so that we can understand these things. And this is what finally brings me to tidal disruption events, stars getting destroyed by black holes. Now, what happens in a TDE is that a star will get too close to a black hole, as in this image here. And what happens next is actually kind of similar to the tides on Earth. So on Earth, there's a difference in the gravity from the moon, the side that's closest to it and the opposite side. This causes the oceans to bulge a little bit in the direction towards the moon and to be compressed a little bit on the perpendicular sides, and this creates the tides as the moon goes around the Earth. This difference in gravity is called a tidal force. That's why we call them the tides. This is also why we call this a tidal disruption event, because what happens to the star is very similar to this. It's just on a much more extreme scale. The difference in gravity on the side of the star that's closest to the supermassive black hole and the opposite side is so great that it stretches into a long, thin strip and gets torn apart. What then happens is, because all of this material is very close to the black hole, most of it gets flung away at a very high speed, and the rest of it remains gravitationally bound and kind of falls back towards it, like in this image. And eventually, we think this will create one of these accretion disks. And all this stellar material, this gas that's left behind, will heat up quite a bit throughout all this process. It gets to tens or even hundreds of thousands of degrees. So because of this, it gives off a lot of light, so much, in fact, that it outshines all the stars in the galaxy where it's happening, all of them combined. So these are ultimately so useful because they can happen around any black hole, even these dormant ones that I mentioned before. And because they last for only a few years, they let us see these processes happening in real time. We can see the disk form. We can see it get destroyed and get consumed. And we can't do that with those active galactic nuclei. So just to show you what this might look like in movie form, this movie shows a recent simulation of a TDE. The star that's going to be disrupted is indicated with a circle, and the black hole is indicated with an arrow. So what you can see is that you get this huge tail of material that gets flung away and expands out far distances. And then near the black hole, this material doesn't just fall directly back into it. It comes back around. It orbits the black hole many times, which causes it to crash into itself. It puffs up, it ejects more material, and it creates this sort of shell of gas around the black hole. If we zoomed in really close, you might see an accretion disk starting to form. And you can see here, the dynamical picture of what's happening in one of these TDEs is really complicated. And it turns out that really small changes to the things involved here, for instance, increasing the mass of the black hole just a little bit, can result in something very different. For instance, this picture on the right is a totally valid other simulation of a TDE. The fact that this can change so much makes it hard to accurately do these simulations and know what's going on. Typically, what we have to do is make some simplifying assumptions, and then what we'll do is run lots and lots of simulations at once, where we keep everything the same except just one property, something like the mass of the black hole. Maybe we'll increase that a little bit each time. So then by looking at how those simulations change, we can learn how a more massive black hole might affect what happens in a TDE, or what might happen if the star got closer to the black hole, for instance. Okay? Now, why am I talking about simulations? Why don't you just go take a picture of one of these TDEs and see what's happening? Well, we do take pictures, but unfortunately, I think they're a lot less exciting than you might imagine. This is a picture of a TDE. So the image on the left here is the galaxy where this TDE happened before it happened, and the image on the right is during the TDE. So you can see really the only change here is that the middle of this galaxy gets a lot brighter. This is because this is actually a really far away galaxy. It's about 300 million light years away. And unfortunately, this is one of the closest TDEs that we've ever found. Because it's so far, we just can't resolve what's happening in the center of it. If we could zoom in with some crazy future telescope, maybe we'd see something like this at the center, right? The reason we have to look at distant galaxies is that these TDEs just don't happen very often, probably about once every 100,000 years in a galaxy like the Milky Way. So even if we stared at the center of our own galaxy for our entire lifetimes and had many future generations do the same, we probably would never actually see this happen here. The only way we can find them is to look at a lot of galaxies, and that means looking farther away. However, we can still identify TDEs and learn about them just from images like this. If we keep taking images of this galaxy over time, for example, we can see how the brightness is changing over time as the TDE happens. We can make a plot like this. This is the only plot of actual data I'm going to show you, don't worry. Now you can see here, this galaxy wasn't really doing anything for several months, and then the TDE happens, it gets brighter over time, and then it fades away as this disk gets consumed. Just this alone is enough to help us identify this as a TDE. And using plots like this, we can infer things about the black hole. So to put this all together and show you what this looks like, this video is going to show images on the left as they get progressively brighter, this plot in the middle of the brightness over time, and then on the right, a simulation, something that might be happening in the middle. So what we do is we watch the galaxy get brighter, we map out how much brighter it's getting, and we go and compare it to our simulations. Remember, I said before, we do lots of simulations where we vary the parameters a little bit. So from those simulations, we can get sort of an expected curve, what this might look like for that given simulation, and we can compare the actual data to that model. We can find the one that fits it best, and from that, we can assume that the TDE probably looked something like this simulation. In this case, that meant that the supermassive black hole responsible for this tidal disruption event was about 6.9 million solar masses, almost 7 million times the mass of our sun. Okay? Now, this isn't all that we do. We can take other types of observations and compare them to these models as well, and learn more things about the black hole or about the star or what happened in it. But this is an example of how the light from the TDE can tell us something about the black hole responsible for destroying the star. Furthermore, this isn't a solved problem. As I mentioned before, we have to make some assumptions when we run these simulations to get them to finish in time. So if we want more accurate ones, what we need to do is compare them to more data. So observational astronomers like me will go and find and study more of these tidal disruption events, and then we'll go compare them to our simulations. We'll find the areas that look good, we'll find the areas that don't match or that show things that the simulations never predicted. And the theorists and the simulation people will take those data and figure out new models that can explain it. That comes back to us, and we just keep going in this cycle. Every time, getting a better and better understanding of what's going on. So ultimately, these TDEs can be powerful tools for studying black holes, but we need to keep finding more of them. We need to keep observing them in as many ways as we can so that we can accurately go from something like this to something like this. All right, so we've gone through a lot here. We've talked about general relativity, what black holes are, how we find them, and how we can study them using tidal disruption events. So just to close, I want to bring things back to black holes and give you a few fun facts to take home and wow your friends and family with next time you're able to hang out, okay? So black hole fun fact number one, a black hole with the mass of the Earth would have an event horizon the size of a pea, and the supermassive black hole at the center of our galaxy, which is about 4 million solar masses, is almost as big as the orbit of Mercury. So you can see we're talking about very different scales here. Now, the most massive black hole we've ever found is about 60 billion times the mass of the sun, and it would be about 1,000 times as big as the Earth's orbit. So it would easily encompass our entire solar system. Fun fact number two, the closest black hole is about 1,500 light years away. This is the closest we've found, I should clarify. It's in the constellation Monoceros, the unicorn right about here. So if you look for Orion's belt, it's kind of pointing towards it. This is also the smallest black hole we've actually found so far. It's about 3 solar masses, so 3 times the mass of the sun. Black hole fun fact number 3, based on the number of stars in the Milky Way that will someday turn into black holes, we think there's somewhere between 10 million and 1 billion of these stellar mass black holes in our own galaxy. We also have one supermassive black hole at the center. Given that there are billions of galaxies in the universe, this means that there are potentially billions of black holes out there. Fun fact number 4, Stephen Hawking actually lost 2 separate bets related to black holes. First of these he made with Kip Thorne, and he bet that the first black hole we found would actually turn out not to be a black hole. He conceded that bet in 1990. And the second one, he and Kip Thorne both made with another physicist named John Preskill, and they bet that black holes would destroy all information that goes into them. Now this is sort of a quantum physical question, it gets kind of complicated, but Hawking ended up conceding that bet in 2004. However, Kip Thorne still has not admitted defeat. Fun fact number 5, which is maybe less of a fun fact, if you were to fall into a black hole, we think that before you actually get into the singularity, you would likely be what we call spaghettified. So just like how in a TDE, the difference in gravity on opposite sides of the star cause it to stretch and tear apart, the difference in gravity between your head and your feet would be so strong that you would stretch out into a long, thin noodle. And finally, fun fact number 6, the first actual picture of a black hole was taken in 2017 when a group of telescopes all over the globe worked together to take an image of the supermassive black hole at the center of a galaxy called M87, which is about 50 million light years away. This picture on the left is the actual picture that they took. And the picture on the right here is sort of a model of what this might look like if we had the power to resolve what's actually going on there. So we've now finally actually seen a black hole. We know that they definitely exist. So we've once again confirmed the predictions of general relativity that Einstein made over a century ago. All right, I'll leave this up here and be happy to take questions. Thank you.
All right, Tom, thank you for an excellent talk. We have lots of questions. We'll see how many we can get through here. The first is, you mentioned the merger of 2 neutron stars.
Yep.
Question is, what happens when 2 black holes crash into each other? Would you expect to see anything?
So probably not. We expect probably when 2 black holes merge, they just become a bigger black hole. They do send out these ripples, these gravitational waves, which we can look for and detect with these special detectors on Earth. But in terms of light, we probably won't see anything. However, that's not 100% sure. We are still looking. So every time the gravitational wave detectors actually do detect one of these happening, we do take our normal telescopes and go look to see if we can find something coming. But so far, we haven't found anything yet.
Great. A question from Richard. Are there supermassive black holes that either never were or are no longer associated with galaxies?
Yeah, that's a really good question. It's not one that we have a great answer to. Part of the problem is we're still not really sure how these form, right? So the reason that they're at the centers of galaxies, we think, is because there's so much stuff concentrated into such a small space at the centers of galaxies that the conditions are more conducive to forming one. But it's possible that way back in the early times of the universe, things were different and somehow these were able to be created. The problem is if they're just floating out there in space, there's no way to actually see them because they're dormant and they're just, they're not taking anything out. So there'd be no light coming from them, so we don't know. Fortunately, space is really big, so we're probably not going to run into it.
So you mentioned in your talk, you were talking about kind of how far out the black hole impacts material. So there's a related question here. Mm-hmm. You know, if a black hole can chomp on a star, could it tear a whole galaxy apart?
I mean, in theory, it could take in all the matter that's in a galaxy, sure. The problem is galaxies are really, really big. For instance, just to get to the center of our own galaxy, it would take tens of thousands of years because they're very far away. So even at the center of our galaxy where things are densely packed, there's a lot of empty space. So for the black hole to be able to keep eating the whole galaxy, it would have to basically have a continuous stream of matter to keep falling into it so that it could keep growing bigger, right? So in theory, yes, you could have a black hole that just keeps growing and growing and growing and growing. And maybe over time, all the stars in our galaxy someday will all fall in billions and billions and billions of years. But I think that would be a very slow process and probably pretty unlikely to happen given how empty space is.
Well, that's good for us, right?
Yeah, definitely good.
Yeah, so there's a question as to why TDEs are so rare or so uncommon.
Yeah, so this has to do with just how close you have to get to one of these supermassive black holes for this to happen. So you can get very close to one and still be able to orbit very stably. Like in that video I showed, there are a couple that are orbiting pretty close. The problem is you just have to get very, very close to it. And usually we think that the way this happens is you might have several stars orbiting this supermassive black hole. And due to those stars kind of affecting each other's orbits, one of them might get pushed closer to the black hole. Basically, it's just a process that takes a long time, we think. And because of that, it just doesn't happen very often. Now, it's possible that in certain situations, for instance, galaxies can merge. And when that happens, you might end up with a lot more stars briefly towards the center of the galaxy. And in that situation, they might happen more frequently. We think that in some types of galaxies, they actually happen as often as one every 100 years. So still a long time, but something that in theory we could actually observe if our galaxy was like that. But unfortunately, it's not.
So let me just ask one last question,
Sure.
and then we'll wrap up here, which is, what, in your opinion, what is kind of the biggest unknown about black holes? Or if there's one thing you could know, what would it be, I guess?
I mean, I think I have to say that it would be great to know what actually happens at a singularity, you know? I mean, I think it is a little bit far-fetched, but it is theoretically and mathematically possible to say that you could fall into a singularity and go back in time or go somewhere else instantly. And, you know, when we encounter infinities in physics, it usually means we don't understand something. And I think it would be really interesting to know what actually happens there. What is a singularity exactly? What does it mean when there's nothing, no volume, but you have masses like 1 billion times the mass of the sun? I think that would be the question I would love to know the answer to.
Yes. Well, it's good because it gives the Hollywood lots of opportunities to make stuff up. Excellent. Well, thank you, Tom, again for a really great talk. And thank you, everybody, for joining us. I want to remind you we're back in 2 weeks with a topic will be binary stars, which we heard a little bit about today. You'll hear more about that in 2 weeks, so please join us then. Thank you.
All right, thanks so much.
Thanks again, Tom.